You're listening to the N2K Space Network.
Welcome to T-Minus Deep Space from N2K Networks. I'm Maria Varmazes, host of the T-Minus Space Daily podcast. Deep Space includes extended interviews and bonus content for a deeper look into some of the topics that we cover on our daily program. IENAI Space has designed a palm-sized propulsion option for future space missions. The electrospray technology is being developed as a cost and mass-effective method of propelling CubeSats and other small satellites. For the first time in Europe, this ionic-liquid-based electrospray propulsion system has achieved more than 400 hours of continuous operation. And to learn more about this, I spoke to IENAI Space co-founder and CEO Daniel Pérez Grande and asked where the idea came from to develop this kind of tech.
My name is Daniel Pérez Grande. I'm the CEO and co-founder of IENAI Space. I guess being on a space podcast, I should kind of give some of my credentials. So I am an aerospace engineer. And then after working for a few years in the industry, I went on to do a PhD in nuclear fusion and plasma physics. But that was with an application in particular for space propulsion technologies. And in fact, that's where I met the rest of my co-founders at IENAI Space. And once we finished our PhDs, we were, I guess, very aware that academia was not necessarily where we wanted to be, and for the rest of our lives, it wasn't where the most exciting stuff in space tech was happening. So we decided to start a company, and and almost 5 years later, that's where we are.
So tell us a bit about what your company does and what you all are working on.
IENAI is a space mobility company. I'd like to mention, by the way, that the word IENAI comes from Greek. You mentioned, Maria, that you're originally Greek. It's Old Greek, and it's the word that we used to derive the word ion in Faraday. Michael Faraday used that to derive the word ion, which are charged particles, right? And we do ion propulsion, right? So our core products are centered around ion propulsion. So we thought it was kind of like a good reference to that. In fact, in Old Greek, it means to go, right? So to go with ions, I think it's kind of like it really makes sense as a name for the company.
You get brownie points from me for that. Not that it counts for anything, but I love that. So thank you.
Okay. So we're a space mobility company. Our core products are around ion propulsion or electropropulsion, as people know it in the field. But we're not just a propulsion company. We like to say that since we have a lot of core know-how around propulsion, around flight dynamics, around maneuvering in space. There was a lot of, when we started the company, there was really a lot of pain points that we were seeing in the industry that could be solved by bringing that knowledge into basically satellite builders. So we do propulsion, but we're not just a propulsion company. We are actually creating an ecosystem of products, both hardware and software, to really streamline as much as possible every aspect in the mission related to propulsion. And in fact, because propulsion can be quite critical for any space mission that's worth its name, basically, you really need to start looking into it as early as possible in the mission. So we have a software that can help you during your mission analysis and definition, can help you select the right propulsion system, can help you understand your propulsive requirements. And we're also going to start developing this year a software for operations focused on space mobility. So I like to make the analogy that, if you're building a spacecraft, if you're building a satellite, right, you're not going to go and tell the rocket launcher what's the best trajectory to take, because that's a completely different field, right? But you do have to integrate a propulsion system in your satellite, and you do have to then choose what are the best maneuvers for that, right? So we want to help those spacecraft builders, those spacecraft operators with our core know-how, which is related to propulsion, to carry out those operations. So in that sense, we're able to kind of really join or help our clients really at the beginning of their missions all the way towards the end of the mission.
Well, that's a fascinating proposition there. So tell me a little bit about what makes you guys different. So I saw the word miniaturization in there. This is sort of a little taste of that. Tell me more about all that. That's really neat.
Yeah. So when we started about 5 years ago, I think CubeSats, right, were all the rage. Everybody was like trying to do CubeSats. There were people doing even pico satellites, which were smaller than CubeSats, right? And there's a lot of like business models being built around that. I think Planet very famously, kind of has sent up something like 450 CubeSats out there, like on the Doves, right? And I think people are now moving towards larger things. But at the time, that there was a lot of interest in miniaturization. And in fact, I have to tell you that the miniaturization of particularly electropropulsion systems, because chemical propulsion systems are a little bit different, unfortunately, because they consume quite a lot of propellant, you can't really miniaturize them that much, because at the end you still need to carry that propellant, that minimum amount of propellant, so that you can actually do your mission. Yeah, exactly. So you can do your stuff, right? But electropropulsion was actually brought into as a technology because it saves a lot of mass. But when you start miniaturizing those propulsion systems, traditionally those electropropulsion systems, particularly those based on plasmas, so people might recognize Hall effect thrusters or gridded ion thrusters. Unfortunately, the efficiency of these systems just goes really low. It's basically, we joke internally that they're really expensive light bulbs. And this is, I'm probably going to get a lot of people out there mad at me for saying this, but you look at them and they look really cool. You have your plasma beam out there. It's ionized, so it's almost like looking at one of those like cool LEDs or whatever. But you're not really generating that much thrust. So
little puffs, right? Like little,
exactly. It glows. It looks really cool, kind of like this bluish glow. But at low powers, you're just not very efficient. Which is by the way the main KPI for electropropulsion, right? Efficiency. So we came out of university. We didn't have a propulsion that we had to kind of a legacy propulsion that we wanted to commercialize. So we had the freedom to just look into what are the best technologies out there to work. And we found one that was actually, it's very interesting actually. It was developed originally in the 70s by NASA. At the time they were called colloid thrusters. So it was basically using a mixture of salts and liquids. So the liquids became conductive, and through electric fields you could extract those charged molecules, accelerate them under an electric field, and shoot them out and generate thrust. And this was originally developed back in the 70s. At the time, the let's say these systems where they shine is in that miniaturization. And back then, satellites were huge, right? So it wasn't, you just couldn't do anything with these systems. And then in the 2000s at MIT, there were a couple of professors, actually one Mexican and one Spanish, which kind of like started looking back into these type of technologies. And I think the word that was kind of coined at the time was electrospray, which has actually been used as a different technology for other in other fields. And there's actually some Nobel Prizes associated to electrosprays as well. But you can actually very efficiently shoot out these ions. And the core, let's say, at these technologies is that instead of using these plasmas, these really nice glowing plasmas, which unfortunately at low powers are very inefficient in terms of propulsion, you're using a propellant. In our case, we call it an ionic liquid or a molten salt. So it's as if you had basically tabletop salt, right? But instead of being solid, it was liquid. And if you coat with that salt, basically a particular geometrical arrangement, which is what we call the emitter, and you put an electric field on that, you start shooting out ions. And those are the ions that are generating thrust. And the really cool thing about that is that in order to do this, you actually need to go down to the microscale and even down to the nanoscale. So these emitters that I'm talking about, when we manufacture them, we use technologies from the semiconductor industry. So the same technologies that you're using for microfabrication of microchips, we use those to sculpt these geometrical structures that help you concentrate the electric field and start shooting out those ions from the molten salt. And we use those microtechnologies and those nanotechnologies in order to achieve these very compact and very small propulsion systems. And in fact, they are so small that they basically you can hold them in your hand. It's a propulsion system that fits on the palm of your hand. It's a pocket rocket, if you want to use that phrase.
That's dangerous, but yeah.
Yeah, well, that's true. That's true. I hadn't thought about that, but yeah. But in fact, the first propulsion system that we made, the first one that went up, which went up on the Firefly Alpha 2 mission a couple of years ago, end of 2022, was actually not even on a CubeSat. It was actually on a pico satellite. I mean, we can make it that small. And the reason for doing that was because we wanted to really explore how small could we go? How small can we make this technology? Because in the same way as microchips, where you're basically manufacturing hundreds of them or whatever, right? The good thing about this technology is you can manufacture these kind of like single propulsion units, and then you can add more or less depending on how much thrust you actually need for your mission, right? And that efficiency is going to be independent of the amount of emitters that you add to your propulsion system. So we have a propulsion system that is focused on miniaturization thanks to this electrospray technology, which is built with micro and nanotechnology. But the key characteristic, aside from the fact that it's extremely efficient at low powers, is that it's also customizable. We choose the number of electrospray emitters. We choose the amount of propellant that you're going to be carrying to orbit. That means that we can cater particularly to the requirements of our clients, both from their mission and platform perspective. And I'd like to add that, in fact, we've also built other products that help us do that. So we now have a software, which is actually our first product on the market. It's called 360. It's a space mobility and mission analysis software. And what that software allows us to do is to basically look at your problem, look at your mission, and help you decide. Listen, if you want to go for a chemical propulsion system, you can also do that. The software enables you to study those kinds of systems. But if you want to go with us, we can tell you exactly what configuration of the propulsion system you're going to need and the best one to fit your mission and platform.
We'll be right back after this quick break. My goodness. One of those on its own would be impressive, but the fact that you're doing many of those is quite a lot. That is super cool. When you were talking about the semiconductor, especially part, I was thinking about the crystalline structures that are used with wafers, and I sorry, my brain went down that rabbit hole a little bit.
There's an article, right? There's an article that phys.org came out last week actually, on our propulsion systems, and it's very cool because you can actually see the picture that we have there is a hand holding a wafer, and that we use semiconductor technology to manufacture our propulsion systems, and they're manufactured directly on silicon wafers.
Oh my gosh,
it's pretty cool. Yeah, it's it's one of these things where I'm a big science fiction geek, and on all those movies when you see something that resembles like a spacecraft, and then you see the propulsion system, and you're like, this doesn't look like any propulsion system that I've ever seen in my life, right? It's not a rocket. It doesn't have, whatever. The first time I saw a SEM, so a scanning electron microscope image of our micro propulsion emitters, right, or electrospray emitters, which have to be imaged at the micro scale because otherwise you can't see them, I thought, this doesn't look like anything like any propulsion system that I've ever seen, right? It was a big kind of like sci-fi geeky moment for me because it was like, this is kind of science fiction a little bit, you could see it and you wouldn't imagine that that's ever going to be used for propulsion, but we are generating thrust in our lab and hopefully in the future and many satellite platforms out there.
It is so fascinating. We will definitely link everything you've mentioned. It'll be in our show notes for listeners who want to take a look because that picture is really fascinating. And also just what you said. As you were walking me through it, I'm going, that definitely, I've never heard of anything quite like that, but it is fascinating. So congratulations to you and your team. This is really cool.
We're excited by it too.
I can imagine. Just fascinating. So yeah, tell me about what you're working on now, maybe who you're working with, any partnerships that are of interest you want to highlight?
Yeah. So, we're based in Spain, although we have also offices in Sweden, in north of Europe. We are actually planning to move over to the US as well in probably next year. So we do want to open up, some offices there and potentially move some of the manufacturing also towards the US. We're very much aware that the US market for space is the biggest market out there. So that's something that we need to do as a company. But we wanted to do this at the right time when the products were already kind of like tried and tested and we had product market fit. At the end, we are a startup. We need to demonstrate the same thing as other startups, product market fit, scalability, that kind of stuff. So we wanted to do that at the right time, especially because in the US, there are companies already kind of working on propulsion. So we couldn't be just like the newcomer and just like saying like, oh, it's going to be 2 years until we have the product. We wanted to go out and have the product ready. So we, in order to do that, going back to where we are right now, so we have one software that's out in the market. We're basically, we did a closed beta for the software last year. We had about 35 companies from the industry. Actually, a couple of them were American as well, testing out the software. They provided us a lot of good feedback. We're implementing that now, and we actually released the software tool commercially end of last year, and we have a few clients now that we're starting to onboard into the tool. So that's very exciting time for the software team. Hardware perspective, we just actually passed a major milestone. So end of last year, we demonstrated. Yeah, thank you. So we demonstrated that the thruster could operate for 400 hours straight. And in fact, we didn't do more hours because we didn't expect that particular test to be able to run for so long. So we just didn't put enough propellant. We just didn't put enough propellant into the thruster. But we demonstrated, 400 hours operation. And the critical aspect always with electropropulsion is your lifetime. You need to be able to deliver thrust because you're delivering very little thrust, very efficiently from the point of view of fuel, right? So it consumes very little propellant. Sometimes it doesn't generate too much thrust. That's why the efficiency of the system, the overall efficiency is so important. But you're delivering that kind of like small amount of thrust, but you need to do it over a long amount of time. And then lifetime becomes the second most critical KPI after efficiency. If you look at a lot of the companies that are out there, a lot of the startups, of course, we're not the only ones out there trying to deliver an electropropulsion system. You ask them about the lifetime, and kind of like the conversation goes a little bit quiet. So 500 hours is really the minimum. So we did 400 hours. 500 hours is the minimum commercial amount of time that we know that we need to have in order to deliver a commercial thruster. So one that can actually carry out missions in space. 1,000 hours would actually be the actual target that we would like, and then we're hoping to be able to raise it to about 2,000 hours of operation, continuous operation, which then would put us with basically up there with most of the propulsion systems that are worth their name, basically. So in order to do that, we're currently carrying out a technology maturation process or program for. We call our propulsion systems Athena. It's adaptable thruster based on electrospray powered by nanotechnology.
Love all these Greek names, by the way. Just really appreciating that.
It's exactly. Or mission patch is kind of like Athena, kind of like holding one of our thrusters. So it's very cool.
Thank you for that.
And so we have a technology maturation program for that right now. We just passed that major milestone, and ideally we are going to be releasing the thruster commercially towards the end of the year. What we have planned for this is, at the moment, we have booked 2 space missions with 2 European companies to fly 2 thrusters at the end of the year. And what we're trying to achieve here basically is not to come out to the industry and say like, hey, look, we flew once, now we have a product. Nobody really believes that anymore, right? So you need to demonstrate and demonstrate and demonstrate. And so we at least have these 2 missions now, and we're planning at least 2 more missions in early 2025. But we're sure that, with these 2 missions already playing out, we're going to be able to give enough confidence to our initial clients to, I think, really take the risk on just what we see as a better technology, just a better propulsion technology compared to what's out there right now. And in fact, we already have a few companies that have reached out and are kind of like in line to purchase, let's say, the first thrusters that we're able to deliver. So it's exciting times for the company, to be honest, very exciting times. But you mentioned at the beginning of the podcast that, 5 years is a long time for a startup. Space tech startups, obviously take a lot of time to build that product. I think I always mention it as kind of like a double-sided sword, right? Like we were very lucky in the sense that we didn't have any legacy technologies that we needed to kind of like bring to market, because I think that would have fundamentally biased us in choosing the right technology for the market. But that also meant that we had to develop everything from scratch. So that's why it's taking a little bit longer than we wished. But yeah, we're still healthy as a company, and again, closing our first contracts for the software for 360, and putting in place the first contracts for the propulsion system Athena as well.
Honestly, it's very impressive. And one of the last startups that I worked at, we always joked that we would age in dog years for every year we worked at the startup. So exactly. Seriously, It's incredibly impressive what you're working on, and I wish you all the best. And I look forward to hearing more about how things go. So please definitely stay in touch. I want to make sure, because you've given the awesome pitch and told us about your market and your plans. I want to make sure if there's anything you want to conclude with to let our audience know more about you, or anything you want to let them know. I just wanted to give you that opportunity.
Sure. If you're interested in what we're up to, just check us out at IENAI.space. Very easy to follow. That's IENAI. I know the spelling is a little bit more difficult, but again, Greek Greek words. You can follow us on LinkedIn as well, and we do try to tell a lot about, or tell the community a lot about what we're up to. You can also catch us next year at SmallSat Conference in Utah. We're going to be out there, and hopefully we can figure out more partnerships and figure out how to get more of our propulsion systems, or micro propulsion systems, microfabricated, and silicon thrusters out to U.S. companies, which that would be amazing for us. So looking forward to talking to anyone that's interested.
That's it for T-Minus Deep Space for January 13th, 2024. We'd love to know what you think of this podcast. You can email us at space@n2k.com or submit the survey in the show notes. Your feedback ensures that we deliver the information that keeps you a step ahead in the rapidly changing space industry. This episode was produced by Alice Carruth, mixing by Elliot Peltzman and Trey Hester, with original music and sound design by Elliot Peltzman. Our executive producer is Jen Iben. Our VP is Brandon Karp. And I'm Maria Varmazis. Thanks for listening. We'll see you next time.